we're doing today. Okay, so I'm going to go to Zybooks here, and you see, last week we kind of talked about the division algorithm, and we learned of things that different things like how to find how to work with the mod function and how to work with the div function and so on. And we learned a lot of just some basic vocabulary that probably you already knew about. And then of course the prime factorizations. We talked about that, where if you need to take any number and factor it, what you can do is start at the top and then draw a little tree, keep finding numbers that you need to multiply together to get that number at the top, and then you kind of make this tree, and then at the very bottom, when you go as far as you can on each branch, then you would have the prime factorizations, right? So we learned how to do that, and we learned that if we did that, then it's very easy to find the greatest common factor, because we could look at the prime factorizations together on two numbers, and then from that determine what the greatest common factor, or as the book calls it, greatest common divisor is. Okay, so and then we also found that you can also use another rule that's similar to find what the least common multiple is, again by looking at the prime factorizations and comparing the exponents of each of those prime factors and determining the LCM from that. Okay, so we learned all of that, and we're learning all of that for a reason. We're learning that so that we can eventually next time talk about cryptography. So I'm going to show you here 4.4. Hopefully that will be something we can get to on Wednesday. And I'm going to open it up just for a minute and show you something here. So it talks about the RSA crypto system. We're going to find that it's a really good system that's hard to crack. But look at this. How do you find it? For RSA, it says preparation, and don't worry about this because we're learning this next time, but I wanted to say right here, computes the multiplicative inverse of two numbers here, E mod phi, or I think that's what it is. I forgot what that's called. But anyway, you're going to have to find the multiplicative inverse when we get to working with this RSA crypto system. And so today, pretty much the whole time, we're going to be learning how to find the multiplicative inverse of a mod function. Now, it's not as easy as you might think. So we're going to go into it. It's going to take the whole day for us, this whole class period, to learn an algorithm. And then the first algorithm that we're going to learn is fairly simple, but then we need to extend it so that we can even do more with it, so that we can eventually find that multiplicative inverse. So that's the whole goal, is to find that multiplicative inverse. And we might not even get to that part today. We'll see. But that's where we're going. That's why everything we talk about today is necessary. Okay. So let me get started with this PowerPoint. Okay. Okay, so we're going to talk about 4.1 and 4.2 today. 4.1 had some interesting things in it, but 4.2 is the one where we need to learn this algorithm, and I want you to be able to learn it well. I want you to be able to see a lot of examples. So because of that, I figured it was going to be taking pretty much all class period to cover 4.2. So what I decided to do was boil down 4.1 into what you need to know. And I'll just tell you, you're not going to have to do any of the participation. I think there's maybe only one participation activity anyway from 4.1. So you're not going to have to do that. I had some slides already ready to go, but then when I found out that 4.2 is going to take so long, I decided, okay, let's only talk about the necessities, what we really need in order to use once we finally get to the cryptography part. So what I'm going to do is for 4.1, I'm going to kind of give it to you in a nutshell, tell you all you need to know for it. And as I said, there won't be any assignments from that, and you won't really be held responsible to know the details that you would have learned in 4.1, since we're just, but there is a bottom line I want you to know from this, okay? So 4.1 is called factoring and primality testing, okay? So they start out by telling us that in cryptography, again, what we're getting to eventually, that makes use of some very large numbers. And some of these numbers can be very large and on the order of several hundred digits. Now this, they said, consider this number here. That's not even several hundred digits, right? Maybe 1, 2, I don't know if it's even 100 digit, maybe it is. But I mean, you know, that's one big number there, but it still doesn't have several hundred digits in it. So you can imagine, you know, we're going to maybe be working with these very large numbers, and part of that would be we would maybe hope. Well, it all boils down to finding factors and greatest common factors of different large numbers. And so we would hope that maybe there was an algorithm that where we could take any number this big even, and possibly run this algorithm in order to find some factors. You know, even if we're not going to find all of the factors, if we just had an algorithm that would, you know, at least find if it's prime, then tell us it's prime. Otherwise, say, well, here's two numbers that are multiplied, you know, besides 1 and the number itself, that when multiplied together give us that number. Ultimately, that might be something that we would want to be able to do if we're working with very large numbers like this, and if we were wanting to crack a code, okay? So what if we had to factor that number? So one of the things that they did in 4.1 was talk about this brute force algorithm, where you just basically start at 2. Is it divisible by 2? Is it divisible by 3? And go all the way up, keep going until you go as far as you need to in order to be able to find at least one factor besides 1 and the number itself. But it turns out that algorithm for a large number would be very inefficient and would take a very long time. The book even said, assuming that one of the steps in there was, you know, took a nanosecond to do, it said that for a large number, that algorithm would not even, it would take our lifetime to run. Okay, so that's not very efficient. So it turns out that in general, there is no known algorithm for solving this factoring problem for these large numbers, for any number. And, you know, we would have to know that it would need to work for a large number too. No algorithm that can be, that's efficient, okay, that's doable, you know, in a short enough time, okay? So that's good for RSA encryption, because that's why it can be used. Because the reason, and this is what the book says, the reason that the RSA encryption scheme that we'll cover next time is used with such confidence to transmit sensitive information is because researchers believe that there's no efficient algorithm for factoring. Okay, so if there were, then, you know, someone who's trying to crack the code could run this algorithm, find the factors that's needed, and then continue on. Okay, so that's not going to be possible though, because of this problem. And so that's good if for whoever wants to use the RSA encryption scheme. And so again, we'll talk about that next time. But for now, all you need to know from 4.1 is just that fact, that we can't come up with an efficient algorithm for factoring, and that's all. Okay, so again, don't worry. There's one participation activity, but I won't hold you to having to know how to do that. Okay, and it's not part of the assignment for week 4. Okay. Okay, any questions so far on that? Okay, if not, then let's go on to 4.2, and this is where we'll spend most of our time today, all the rest of the time that we have. We're going to learn how to perform an algorithm called Euclid's algorithm, and then that one's not going to be very difficult. It'll be fairly easy, but then we'll also need to learn how to perform the extended Euclid's algorithm, which is a little bit more involved, but still, I hoped that you'll be able to see enough examples today, and then be able to work on some examples on your own as part of your assignments. I hope then that this, even though today at first, hearing about this, it might seem a little bit, like, oh, what do I do next? And, not sure what to do. After you see enough examples, hopefully it'll all make sense and you'll be able to do it pretty well. Okay. Let me start by what the point they were making here at the beginning of this 4.2 is that, it's just as we said, there's no known way to find the, well, what we just said earlier is just find two factors, but they're saying even more so. It's no known way to compute the prime factorization of large numbers, where it would be like doing the tree and finding, reducing that number down to a bunch of prime factors.